Hi everyone, it's Miss Billingsley. Today we're going to be looking at the 1.K2.1 notes on transformations in the coordinate plane. Okay, so first let's define what a transformation is. That's some sort of change to a figure or a function. But the main key word here is change. We're changing a shape in geometry or changing a function in algebra. You may even transform yourself. So there's lots of different meanings of that word, but the root of it brings us to that change. So today we're going to be looking at an example of a triangle on our coordinate plane. So first let's go ahead and get that triangle on our paper. We're going to give it the coordinates A, B, and C. Okay, those points are going to be the corners of our triangle. So A is located at -4, 5. Okay, that's right here on our coordinate plane. Let's label it A. B is at the point -6, -4, which is down here. Let's label that B. And C is at the point +4, -4, right here. Okay, and we'll label that C. Let's connect our dots. So here's our triangle ABC. This is the shape that we're going to be transforming using our instructions below. So first, let's take a look at a translation. The way that we describe a translation on a graph is some sort of movement. Okay, so we'll just say it's a move. We're shifting it around on the graph without changing the size of it and without changing the orientation. So here's a little visual example for us. And what I mean by orientation is if this triangle had the points A, B, and C, the way that we read A to B to C is clockwise, okay, all the way around A to B to C. When we move it around, that orientation doesn't change. So here's our copy after its transformation of the translation. And we still go from A to B to C clockwise. So that's what orientation is, the way that we read the vertices of a shape or those corner points. So as a note to self, the size and the orientation stay the same. This is going to be handy for us to use later, so let's go ahead and write these notes down. Size and orientation stay the same. Okay, now we're actually going to perform a translation. Okay, our instructions are here. Translate triangle ABC down 7 units and right 3 units. That's pretty straightforward. We just need to take it one at a time. So we're going to look at each of our vertices, A, B, and C, and move each one down 7 and to the right 3. So let's do that together. Let's count down 7 from A. Okay, and we still got to go right 3, so I erased my dot there. There's where it lands. What's that coordinate point? Correct. It's at -1, -2, and we're going to give it a label of A prime. That little dash mark on the top. Can we see that there? That little apostrophe lets us know that it's a copy of A. Very good. Now we need to copy B by moving it down 7 and to the right 3. I'm not going to draw those lines in, but feel free to. It ends up right here. Okay, let's label that B prime. And we'll do the same with C, down 7 and to the right 3, right here. And we'll label that C prime. Again, I'm going to make my pencil a little bit thicker and connect my dots. Notice that the shape looks the same, the angles look the same, it's just been moved. Okay, that copy's just been moved around on our graph. That is a translation. Let's go ahead and look at a reflection. This is kind of like a mirror image. Okay, and typically we're given a line to reflect a shape over in geometry, like an axis or an actual line like y = 2. Okay, so the size again is going to stay the same. And let's investigate the orientation. If this one here is ABC, our original, and we reflect it over this line here, we get a shape that turns out something like this. A is still on top. That right corner, that right angle corner, is the point C prime, and then B is here. So our orientation actually changes. Notice that clockwise on my original, I go from A to B, but clockwise on my copy actually goes from A to C. So that lets us know that our orientation has changed. Our orientation changes when we have a reflection. Okay, let's actually perform a reflection. Our example says to reflect it across the y-axis, which is this one here, our vertical axis, up and down. And the way that we do that is counting the distance from each of our vertices, A, B, and C, to that line of reflection. So we're looking at this line here. I'll kind of dash it in for us. Okay, and counting the distance, in this case, just horizontally. Notice that A is 4 units to the left of our y-axis, so the reflection is going to be 4 units to the right, all the way over here. I'm going to call that A double prime since it's our second copy on this graph. I'm just going to clean up my lines here. We'll do the same thing with B. Notice that B is 6 points to the left of our line of reflection, so it needs to be 6 units to the right. That will be our B double prime. And then C is currently 4 units to the right, so the copy will be 4 units to the left on top of that line there, and that's okay. All right, let's connect our dots from A to B to C and back to A. All right, notice that's a mirror image. If we put a mirror right on our y-axis, we would get that blue triangle back. Okay, that is a reflection. Just count that distance. Okay, a rotation. A rotation we call a turn. Sometimes it's just a turn. Okay, our size does not change when we rotate. And neither does our orientation. It actually stays the same, despite it looking a little bit different. From A to B to C is clockwise, even if we turn the shape. Okay, A to B to C is our right-hand corner. They're just in a different location, and that's okay. So our orientation is the same. So same rules as the translation, just looks a little bit different. Same size, same orientation. All right, our example says to rotate triangle ABC 90 degrees counterclockwise about the origin. So I'm going to put a little blue dot here. Our origin is that center point 0, 0. Just as a reminder, or in case you didn't know, the origin is 0, 0, the coordinate. Okay, and this one is a little bit tricky. We actually can turn our paper to help us out, but we actually are going to turn it the opposite way. You may want to make yourself a note of that. If we want our shape to turn clockwise, we turn our paper counterclockwise and vice versa. So in this case, we want our shape to go 90 degrees counterclockwise. So that means I'm physically going to turn my paper clockwise. Okay, so what we should be looking at is a graph or a coordinate grid that's reoriented. So I'm going to relabel just to keep things straight in my head. What used to be my x-axis is now my y, and what used to be my y is now my x. See my navy blue drawings? Your paper should be turned. I can't demonstrate it using the iPad, but I'm going to write the other way so that you know what I'm doing. So this is going to force our shape to go counterclockwise. This is the easiest way to perform these rotations. Okay, and the way that we can do it is by counting the distance from the origin to each of our original points. So I'm going to reorient my paper back to normal, and I'm going to say how far away is A? Well, it's 4 units to the left and 5 units up from my origin. Okay, 4 left, 5 up. I'm going to return my paper to the right, okay, clockwise. And I'm going to use my new axis and count 4 to the right and 5 up. No, sorry, left. I keep saying right, but it's left. So 4 left and 5 up. So A triple prime is going to end up right there. That's at the coordinate -5, -4. Okay, and I wrote that sideways. I'm going to zoom in. Maybe. Hello? There we go. Okay, see that now my orientation is a little bit different. I know the video is kind of funny right now, but I can't demonstrate by turning my iPad. Okay, so A triple prime is right there. We should have our paper turned. We're going to do the same thing with coordinate B. So turn back to normal and count the distance from the origin. Looks like it is 6 units to the left and 4 units down. So we turn our paper and count 6 units to the left. I'm going to clean up these guys. Oh no, that was a big eraser. I'm going to clean up the little navy blue lines there. Okay, 6 left and 4 down. That's going to put us right here for our B triple prime, third copy. And lastly, we need to do point C, which is 4 units to the right and 4 units down. Okay, so we'll turn and repeat that. C triple prime, really close to A double prime there, but not quite on the same point. Okay, when we connect those dots, when we turn our paper back, we should be able to see that it's been rotated 90 degrees counterclockwise. And it's been spun around that point, the origin, 0, 0. Okay, so reorient your paper back to normal. And then you can see that it has been rotated counterclockwise. So we always turn our paper the opposite direction that we want the shape to go. That is key. I'm going to reiterate that we should really write that down. That's a really common mistake. Okay, lastly, let's look at a dilation. This is a size change. Okay, so I'm going to put in quotation marks, resize. Okay, it can get bigger or smaller. We can call that an enlargement or enlarge or shrink. Okay, so it can either get smaller or it could get bigger. That doesn't really look that much bigger, huh? There we go. Okay, so obviously the size changes. Notice that this is the only transformation where the size changes. And our orientation does not. Size changes, orientation stays the same. All right, our last example is going to be dilating our original triangle ABC by a factor of 1/2, about the point 210. This one is also a little bit tricky, but once you get the hang of it, it is no big deal. So we're actually going to be shrinking this triangle in half. Okay, it's going to be half the size that it originally was. If it was an enlargement, this number, the factor, would be a number bigger than 1, like 2 or 3 or 5 or 100. Okay, but for this example, we're going to be shrinking our triangle, and it says about the point 210. Okay, what that means is that's going to be kind of our anchor point. So I'm going to go ahead and put that on my graph at the coordinate 210, which is right here. What that does is it either shrinks or grows towards that point. Kind of think of it as like the sun. Okay, it's either going to go towards that or away from it, just depending. Okay, what I like to do is go ahead and use a ruler or some sort of straight edge to connect this dot to each of my vertices. That kind of gives me a visual, because all of our new points have to land along these lines, whether it's a growth or a shrink. Okay, if it shrinks, it's going to be towards it. If it grows, it's going to go away from it, so we can extend those as far as we want. Okay, so because it shrinks, it's going to be getting closer to my point of dilation. And the way that I actually perform this, the way that I do it on a graph, is by counting the distance from each of my vertices, A, B, and C, to that point of dilation. And then I'm going to multiply that distance by my scale factor, in this case 1/2. Okay, so first let's start with A. I'm going to see how far away is it from that point of dilation. Looks like it is 5 units below. And 6, is that right? Did I count right? Yep, 6 units to the left of. Okay, so this distance is 6, this distance is 5. And we're going to cut each of those in half, horizontally and vertically. And that's going to be where our new point lies. Okay, so half of 6 is 3. Half of 5 is 2.5. So that lands right here. And that is our new A quadruple prime point. Okay, for ease of viewing, I'm going to kind of delete all the things that have to do with A, since we now have point A. Okay, we're going to do the same thing for point B, count the distances, and cut those in half. So let's do that together. All right, looks like it's 8 units away horizontally and 14 units vertically if you counted those with me. We need to find the halfway point, and remember, it should lay on that line that we drew in from the point of dilation to B. So half of 8 is going to give me 4. Half of 14 gives me 7. So that B triple prime point ends up right here. Quadruple prime, sorry. Okay, that is the halfway mark between B and our point of dilation. Okay, lastly, we'll do the same thing for C. I'm going to go ahead and clean this up really fast. And we'll do the same thing for point C. I know it's getting a little bit messy, so stick with me. C is the same vertical distance from the point of dilation, so I know automatically that that's 14, just like B was. And it is 2 horizontal units away, so half of 2 is 1. Half of 14 is 7. That point ends up right here. Sometimes you can visualize where half is if you're a visual person. Okay, and our C quadruple prime is right here. I'm going to zoom in so you can see. We'll connect our dots. And now we have a triangle that's half the size of our original black triangle ABC. Okay, it's okay that this point A, ends up in the middle of 2 boxes. That's okay, because when we cut odd numbers in half, it's going to give us a decimal, and that's okay. Okay. All right, now we have performed all 4 of our transformations, and these are some good examples for us going forward. If you have any questions, please let me or Miss Martinez know, and we'll see you next time.